Welcome to Math 222 Week 5 Guidance. This week we're going to talk all about functions. A function is something you've worked with for a long time. You just may not have known what it's called. It's basically a special relationship between values. Each of a function's input values has exactly one output value. So here's some examples here. In this first example, we have the input of zip code and the output of shipping cost. So in this scenario, you're shipping something somewhere, and based on your zip code, you have a shipping cost. If you notice, we have the two first zip codes both cost $5. The third one costs $8. The fourth one costs $10. This is what we call a function. It's a function because for every input, it has one distinct output. 704.54 costs $5. 704.02 costs $5. They each have an output. The other one, for example, is not a function because you have one input here that has two outputs. 49858 could cost $9 or it could cost $12 for whatever reason. So this one is not a function. In order to be a function, you're going to have one output for every input. Just to quickly show you some other examples, in example A over here, we have the first one, which is points x and y. So in the first example, you have x is 1 and y is 2 is your first relationship. In the second one, x is 1 and y is 5. And in the third one, x is 3 and y is 7. In this one, it's not a function because if you look, x1 has two different outputs. So if I was going to map that, 1 would go to both 2 and to 5, so it would be not a function. Part B is a function because each x, 4, 3, 2, and 1 all go to only one different output. So 4 goes to 5, 3 goes to 5, but we don't care that that's a repeat. 2 goes to 6, 1 goes to 7. Every input has only one output. Graphing makes it easy. If you look at a graph, it's easy to tell if it's a function or not based on what's called the vertical line test. I'm going to draw a vertical line at x equals 1. So that vertical line is the input of 1. I plugged 1 into the function, that's my x, and if you look, I have two y's. Y equals 3 point something and y equals negative 3 point something. So this is not a function. If you can draw a vertical line and it touches twice, you don't have a function. Whereas in B, anywhere you draw a vertical line, it only touches one time each, so this is a function. Next, we're going to talk about domain and range. You've heard at least domain before in this class. Domain is the set of all inputs, so what are the values that we can plug into the function? And range is the set of all the outputs, what pops out when we're done. In this first example here, the domain is going to be all of the numbers that we plug in, all of the inputs. So the domain in part A is the set 2 and 4. Whereas the range is all of the outputs, so the numbers that are second, the y's, 5, 7, and 3. In part B, it's a little bit trickier because we have to look at it and say, okay, what numbers can I plug in for x? What could my inputs be? There doesn't seem to be any issues there. I can plug in x equals 1, I can plug in x equals 1,000,000, I can plug in x equals negative 2,000,000, I can plug in 1/17. No matter what I plug in for x, I multiply it by 2, I get a y. Everything seems to work. Same is true for the range. Everything I plug in here is going to pop out another value. No errors, no situations that don't work. The bigger x gets, the bigger y gets. The smaller x gets, the smaller y gets. So this one actually has a domain and range of what we call all real numbers, which is often written with that r right there. And basically just means it goes from negative infinity to infinity without any issues. C is not quite the same thing. This one has a square root in it. Remember, there's no such thing as a square root of a negative number. So we can write x minus 1 has to be greater than or equal to 0. It can't be negative. So then when I add 1 to both sides, I get x is greater than or equal to 1. And so my domain is all real numbers such that x is greater than or equal to 1. My range is a little tricky too. So when we originally did square roots, I told you that the square root of any number was a positive and a negative. That's true. But think about how that would work. If I said that inside that parentheses, inside that square root was a 9, for example, the square root of 9 would be plus 3 and minus 3. That would mean it had two outputs, which would make it not a function. You can only have one output when we talk about functions. So when we do square root functions, we only use the positive square root. That way, we only get one solution, and we can treat it like a function, even though technically it probably wouldn't be. So in this case, we're going to restrict y to being positive, because if it were negative, if I allowed the square roots to be negative, I would have duplicate answers. Next, we're going to talk about function notation. Function notation happens when you replace the y equals something with what we call f of x or any other letter. But basically what this says is that that equation y equals 3x minus 2 is a function of x. X is the input, and f is the function name. Normally we use f, that's the most common, f for function. But if you have more than one function, often you'll see different letters. Like in my example here, I have f of x and g of x, just to note that I have two different functions that I'm dealing with. If you noticed here in example A, where it says f of negative 5, that means instead of x, I want to place a negative 5. So when I write my f of x, I can replace all of the x's with 5s. I want to know what's the function value when x is 5. So I'm going to plug in 5, and f of 5 is equal to 15 minus 2, which is 13. Just so this video doesn't get super long, I'm going to skip B since it's the same thing. If we move on to C, we have f of 0 plus g of 3. So we have f of 0 is equal to 3 times 0 minus 2. I'm looking for what's the value of the function f when x is 0, and that happens to be negative 2. And I also have g of 3. So what's the value of the function g when x is 3? And I get 9 minus 3 is 6. So f of 0 plus g of 3 would equal negative 2 plus 6, which is 4. Now we're going to talk about graphing. I'd encourage you to go into this section in your text. I'm going to do a few examples, but there's a lot more in there for you to look at. The first type of function you can deal with is a linear or a constant function. A linear function is in the form f of x equals mx plus b. These always look like lines. You have a y-intercept, b, and you have a slope, m, and that gives you how much you're increasing or decreasing, and so you get a line. If the mx part is gone, if it's 0, then that's called a constant function, because that means that the function doesn't have a slope. It just stays steady and doesn't go up or down, but rather horizontal. If I want to graph a linear function, I can use that m and b to help me. Since b is -4, that's my y-intercept. So I'm going to go to -4 and make a dot on the y-axis to show my y-intercept. And then 3 is my slope, which tells me that I can go up 3 and to the right 1. So from my y-intercept, I'm going to go up 3 and over 1, up 3 and over 1. I do it a couple times to get as nice and accurate as a line. It's a little hard to do in this surface. But then I'm going to connect those dots, preferably with a straighter line than I just did. And then you have the graph of the function f of x equals 3x minus 4. Notice it passes the vertical line test, so it is a function. The domain is all real numbers because there's not going to be any issue. That line can keep going forever up. It can keep going forever, right and left, up and down. No problems there. So the domain and range are all real numbers. There's 3 other functions that we're going to visit in this unit. The first one is the absolute value function, which takes f of x equal to the absolute value of something. The quadratic function, which we've done lots of in this class, ax squared plus bx plus c, is a function, makes a parabola. The square root function, we've also done a lot of, f of x equals the square root of x. So these are all things you've seen before. Now we're just going to talk about them as functions. So if I wanted to graph this, which is a square root function, same as quadratic functions and absolute value functions, you're going to graph them all the same way. You're going to graph them by making yourself a t-chart or a table of values. So you're going to pick some inputs and you're going to find the outputs for any of these functions. Pick easy ones. 0 and 1 are usually good choices because they're usually easy to work with. In this case, I might not want to go with 2 because I know if I plug in 2 for x, I'm going to get the square root of 5, which doesn't exactly work. You get a decimal, it's no big deal. But instead, I'm going to pick something that has a square root, so I'm going to put in a 6 because I know 6 plus 9 has a square root. I can also put in -2 because -2 plus 3 is 1, and that has a square root. If you don't recognize these, you can pick whichever values you want, and you'll get decimals, but you can estimate your graph. So the next thing you want to do is you want to plug in your values. So you plug in -2 plus 3, and you get the square root of 1, which is 1. And so that's your y value. Do it again for 0. You get square root of 3, which is a decimal, which we said we were going to avoid, but that's okay. It's approximately 1.7, so we'll go with that. If you plug in 1, we get 1 plus 3, square root of 4, which is 2. And if we plug in 6, we get 3. Just going to go through that quickly. So if I were going to graph this at -2, I'm at 1. At 0, I'm at 1.7. At 1, I'm at 2. And at 6, I'm at 3. You should get something that looks a little bit like this. It's not a great graph here, but that's the general idea. It's got a little curve to it. So that's the function. The domain, notice, we could continue our curve, but we can't go underneath the 0 because square roots can't be negative. You're not going to get the square root of the negative number, or it's not a function anymore. So x is actually going to have to stay greater than or equal to 3 as the domain, and the range is going to be y positive. This is what's called a piecewise function. Piecewise functions are when you take two or more equations and have them work at different times. Basically what you do here is for all of the values of x that are greater than 0, you're going to use the square root of x. For all of the values that are less than 0, you're going to use x, negative x plus 2. So if I were making a t-chart here, I'd start with some values underneath 0. So let's see, negative 2, negative 1, and then I'd have some above 0. I'm doing square roots, so I might want to stick with 1 and 4 and 9. So if x is less than 0, if x is negative 2, we're going to have negative 2 plus 2, and you get 4. Negative 1 plus 2 is 3. Now hopefully you also realize that that's a linear function. We talked about that a second ago. So you don't really need to plug in too many values there to know what's going on. At negative 2, I'm going to be at 4. At negative 1, I'm going to be at 3. That pattern, since it's a line, would continue that way. When we get to 0, though, we have to switch functions. It now plugs into the square root of 0, which is 0. Square root of 1, which is 1. Square root of 4, which is 2. And so we could keep that one going too. So we get something like that. One thing I forgot to mention is we have to kind of see how these things connect to each other. So even though this here says that it's strictly less than 0, let's find out what would happen if 0 did plug into that function. We'd get negative 0 plus 2, so that would be 2. So I could keep this line going, except for once I reach that value of 2, I'm going to put an open circle there because that doesn't exist. Instead it jumps down to the other function. But you can kind of see that at least we cover all of the x's. There's no breaks in the x's there. Y is always going to be positive, so that's an issue with our range here. It looks like it's never going negative in either function. So y is greater than or equal to 0. And x is okay, so domain is all real numbers. Now we're going to talk about transformations. Transformations are when you take a graph that you're comfortable with and you transform them. This actually works really well if you can remember the basics of the graphs that you want to work with. So let's talk about what those would be. The very basics, we have y equals x, which is a linear function that goes straight through the origin. I know that doesn't look great, but it's a straight line that goes through the origin. You have y equals x squared, which is your basic parabola. That again goes through the origin. Y equals the square root of x. Again, going through the origin, this time kind of curving sideways. The basic absolute value one, y equals the absolute value of x, is a v that goes through the origin. So those are the four basic ones that we're going to start with. Now, to talk about the transformation, notice here we have that f of x. That's our basic function. So the x squared, the square root of x, or the absolute value of x. If inside your function you subtract an h or any value, you're going to move right if h is positive, and you're going to move the whole thing left if h is negative. So if I did, for example, x minus 2 here squared instead of just x squared, that would be taking that whole graph and shifting it 2 units to the left. If I put a number out front, so for example y equals 3x, I would be stretching the whole graph by 3 units. So it would go up 3 times as fast. Everything would stretch 3 times. It would shrink if it was a fraction. If I put a negative in front, so if that was a negative 3x, not only would it stretch it 3 units, it would also flip it over the x-axis, so it would be a reflection. And then the last thing I can do is a vertical translation, which is moving it up or down, and that's if I, say, add 1 to the end of it. I would take the whole graph and I would move it up 1. Let's try a few. So the first thing we need to recognize is what is the basic function, and sometimes that's a little bit hard to see when we have all of this stuff here. The basic function here is y equals x squared. We know that because we have an x and we have a squared. So that basic function, if I wasn't going to do anything, would be the parabola at the origin that goes like that. So let's talk about what all of this stuff is. The first thing we want to talk about is this up here. Basically what that does is it takes the whole graph and it stretches it by 2, so it goes up twice as fast, and it also reflects it over the x-axis. That's the negative there. So the 2 is a stretch, and the negative is a reflection. So I'm going to go down, but I'm going to go down twice as fast. So I'm going to get steeper. The plus 4 is going to move the whole graph up 4 units. So I'm going to take that red graph and I'm just going to bring everything up 4 units. And then the 3 takes everything and moves it to the left 3 units. So I'm going to take that blue graph and I'm going to move everything to the left. And so this is my final curve, and that was a rough sketch, but the general idea. You can also combine functions, do operations on functions. So in this unit, we're going to learn how to add, subtract, multiply, and divide. This is kind of a chart you can go through real quick. If you're going to add your 2 functions together, you see this notation here. I say f plus g of x really means f of x plus g of x. Same thing with subtraction, multiplication, and division. So let's say I have 2 functions here. F of x equals 4x minus 12 and g of x equals x minus 3. And I want to find the sum of f and g when x equals 2. So the first thing I want to do is find what f of g of x is. So I'm going to add my two functions together. I have f of x plus g of x, where f of x is 4x minus 12, and g of x is x minus 3. Combine like terms, I get 5x minus 15. So that's f plus g of x. But now we want to know what f of g of 2 is. So you get 5 times 2, because x is now 2, and it equals negative 5. You can also do composition of functions, and that is when you kind of combine them together. The composition of f and g is denoted by this symbol right here, read f of g, and is defined by the equation f of g of x, where g is placed inside where x used to be. So if I wanted to find g of f of x, first I'm going to start with the outside function, which is g, and I'm going to take g of x equal to x squared plus 2x. And now instead of x in the middle, notice I have f of x. So I'm going to replace all of the x's with f of x's. So everywhere there was an x, I'm going to put an f of x. And in this case, f of x is 3x minus 2. So now I'm going to do a little algebra to split that up. If I FOIL the first piece, I get 9x squared minus 12x plus 4. And then plus 6x minus 4 for this part here. Combine like terms and I get 9x squared minus 6x. And so that is my g of f of x. Sorry. But notice I still want g of f of 3. So now everywhere there's an x, I'm going to make a 3. So I get 9 times 9 minus 18. 81 minus 18 is equal to 63. So g of f of 3 equals 63. Now on to the second one. Different notation, but same idea. We have f of g of x, which is the same as saying that we want g inside of f. So if I have f of x, and I want to place the g inside of it, I'm going to put x squared plus 2x in those parentheses. Distribute the 3. And this is my f of g of x. And I still want to plug a 2 in. And so I get, let's see, 3 times 4, which is 12, plus 12 minus 2, it's 24 minus 2 is 22. For our last section here, we're going to talk about inverse functions. An inverse function is the function that undoes another function. You've heard of inverse functions before, something like addition and subtraction. If I take x and I add 3 to it, and then I subtract 3, that plus 3 and that minus 3 cancel each other out. They're inverse functions. We're going to talk about inverse functions as one-to-one. It's only an inverse function if the original function is what we call one-to-one. That means that as a function, there's one output for every input, but that there's also only one input for every output. So if you think back to the beginning, if we had a chart here like 1, 2, 3, and here 4, 5, 6, and 1 goes to 4, 2 goes to 5, 3 goes to 6, those would be one-to-one. If, however, I said that 4 also went to 6, I still have a function because every input only has one output, but it's not one-to-one because that 6 has 2 inputs. That means if I were to take its inverse, go backwards, I would have a problem because I would have 2 things going to 1. So we only do inverse functions for functions that are one-to-one. The easiest way to find an inverse is by doing what we call the switch and solve. Basically what you want to do is start by replacing the f of x, or in this case h of x, by y. Then what you want to do is switch the x and the y, because we want to make the inputs turn into the outputs and the outputs turn into the inputs so that we have the reverse inverse direction. So I'm going to change my y to an x and my x to a y. Now solve for y. Divide by 2. So the inverse function of 2x plus 1 is x minus 1 over 2. If I compose those functions, put one inside the other, they would cancel each other out. Just so that we can do one that's a little bit harder, we're going to do the same thing here. First, we're going to change f of x to y. Now we're going to switch all the x's and the y's. So we're going to do x equals y plus 1 over y minus 3. We got to get y by itself. So the first thing I'm going to do is I'm going to multiply both sides by y minus 3. I'm going to distribute this x because that's important here. So I get xy minus 3x. And over here I just have y plus 1 left because those canceled. Now what I'm going to do is I'm going to subtract y from both sides so I can have the y's together, and I'm also going to add 3x to both sides. So now I have xy minus y, and then I have 3x plus 1. Notice we have a common factor here, so I can factor out a y, and I get x minus 1 equals 3x plus 1. So if I divide by x minus 1, those cancel, and my inverse function is y equals 3x plus 1 over x minus 1. So these two functions are inverse functions of one another. Our notation is f inverse of x equals 3x plus 1 over x minus 1. So that's it for your week 5 guidance. It's also the end of this course. Good luck.